Welcome back. This is Dr. Biju Vasudevan, and in this video we are going to discuss the second part of the video lecture for week 13 for calculus 3 in Math211, in which we discuss double integrals over non-rectangular regions. In the previous chapter we have seen double integrals for rectangular regions. Okay, here we have two different types of non-rectangular regions. Type 1 is bound, see, kind of graph that is shown in this here is type 1 region. See, the region is bounded above by a function of x. Y is a function of x, and also bounded below by yet another function of x, isn't it? Y is function of x. So when you draw a small line between these two, its tail end will be function y1, head end will be at function y2. So kind of lines, upper and lower bounds are variables, see curves, but left and right boundaries are straight lines. This is called type 1 region. Let's read the statement now. Type 1 region is bounded left and right by vertical lines. X is equal to a, x is equal to b. Check back the graph, isn't it? X is equal to a, x is equal to b. So left and right are bounded by vertical lines, and bounded above and below below and above by continuous curves. Y is equal to g1 of x, y is equal to g2 of x. So above and below are variables, the limits are variables. Left and right are constant limits. It means that in this left and right, in this direction you get constant limits, in this direction you get variable limits. So your integration will be like this. Double integral, there will be a function of x, y. See, since x direction has constant limits, we will get x as our outer integration, y as our inner integration, in which the limits of y will be g1 of x and g2 of x, where g2 is greater than g1, and the limit of x will be from a to b. So what do you want, for example, if you find integral xy and dy dx, maybe the limit of x from 0 to 1, limit of y may be from 0 to x, some variable should be a function of x when we integrate with respect to y. That is, so in type 1 region, whenever find such a type 1 regions, our integration starts with y, ends with x. So inner integration is with respect to y, outer integration is with respect to x. That's the point. Now can you revert the same point for same idea for type 2? Will you try yourself? What is it? Go ahead to this graph. Left and right limits are curves, variables. We will write x is a function of y, because this direction is for x, and upper and lower bounds are constants. Now y has constant limits from c to d. So outer integration is with respect to y. The constant limits will be the outer integral, right? And inner integral will be with respect to x, and in x you will have y as a variable. X will be a function of y. So that is what given here. In this case you can take the same xy, another example dx dy. The y will get outer limit, which is constant limit, can be 1 or 2 something. For x you can write x2 x square, y2 y square. X will have y as a variable. X will be a function of y. So the limit of x you will find y. So such examples will be integrated with respect to x first, and finally with respect to y. So type 1 and type 2 regions, isn't it? In some cases the graph can be taken either in type 1 or type 2. Both the ways it will be easier. In some cases type 1 will be good, in other cases type 2 will be good. So according to the situation we will choose the best one. So this is what in type 1 region, our integration starts with the y first, where y will have x as its limits. The limits will be a function of x, and outer limit will be with respect to constant. Here in type 2 region, we integrate with respect to x first, and the limit of x will be in terms of y, and the outer limit will be constants. And there is no such situation that both the limits will be variables, both the integrations. For example, f of xy dx dy, you cannot get x to x square y to root y. See, all the limits are variable. This case does not exist for area. When you integrate such functions, you will not end with the constants. The answer will be a variable. It's not possible, right? So there is no such a case where all the limits are variables. There is no such case. So first case, type 1, in which we start integration with respect to y first. Type 2 integration will be with respect to x first. Accordingly, the limits should be chosen from the graph. How to identify the limits? Let's see in practice instead of reading this one. So type 1. So when it is type 1 region, how to find that this is the type 1 region? Just draw one line here, just a strip here, isn't it? Its lower end will give you y1. So this curve will give you lower limit for integration with respect to y first. This is our y1. y1 will be a function of x, and this is g1 of x, and upper limit of this upper end of this line will be falling on another curve. This curve will give you another equation for y, g2 of x. And check how far this line should move from left hand to right hand. What is the limit of x? From here to here, this line should stride to cover the complete portion. So this part you can say a, this part you can say b. So you will get a to b as a limit for outer integration x, isn't it? So if you want to integrate with respect to y first, you should take a vertical strip so that the limits can be identified. Y is a parallel vertical line, isn't it? So when we are integrating with respect to y first, we consider a vertical which is parallel to y, a vertical strip inside the region, so that limits can be chosen. When you want to integrate with respect to x first, differently, you should consider, you will have type 2 region, isn't it? It's coming up here. Where is the type 2? When you want to integrate with respect to dx first and dy second, this should be type 2 region, isn't it? So how to identify the limits, whatever the function given? For type 2 region, x will have variable limits in y, isn't it? So x is a horizontal line. So in this given region, draw a horizontal line which is parallel to x-axis. Its tail and head end will give you lower and upper limits of x. So in this way. So and then how far this strip should move in this direction of y. This is from c to d. That will be the limits for y, outer integration. Some rough examples which is from the textbook. See how the limits of how to find the volume. Volume means we integrate z, isn't it? This is our function to be integrated. So 4 minus 4x minus 2y. 4 minus 4x minus 2y is the integrand f of x comma y, isn't it? Now you can choose either. So see, the region is on the ground, xy plane. This is our region. How to find this region? The region, take z is 0. Z is 0, there is no height. You will fall on the ground, isn't it? That ground has been shown here in the second graph. Now z is 0. What do you get? 4 minus 4x is equal to 2y. When you divide by 2, you will get this equation. Y is equal to, so which is a straight line passing through 1, and you can find x and y intercepts. By taking y equal to 0, you will get x equal to 1. By taking x equal to 0, you will get y equal to 2. So it's a straight line passing through 1 and 2, covering this region in the first quadrant, isn't it? If you want to choose type 1 region, you integrate with respect to y first and next to x, isn't it? Type 1, we take vertical line inside the region. So the vertical line starts from y is 0, y value is 0, ends at y is 2 minus 2x. So this will be 0 to 2 minus 2x. And then the constant limits on this left and right areas will be minimum 0, maximum 1 for x. So integral 0 to 1, isn't it? That's it. If you integrate this one, you will find the volume of this shape. The same region can be interpreted in terms of type 2 region. Type 2, how do you find? When you are looking for type 2, you should take a horizontal line. Double integral, same f4 minus 4x minus 2y dx dy is now. Now x should be in terms of y. So this line will give you the limits of x. Its lower limit on y is x is 0, so x is 0. Upper limit on this line. So find x from here. X is minus 2x is y minus 2. So x is minus y over 2 plus 1, isn't it? So we can write this one. 2x is 2 minus y. So 1 minus y over 2. What will be the upper limit of x? And the range for this direction for constant limit is 0 to 2. 0 to 2. This way you can do in type 2 integration. Fine. Some other examples you can check how the ground, the region over which the volume is found. For this region, this is the given equation. You can find either x or y from this equation as you wish, depending upon the case you choose type 1 or type 2 regions. So all this have been left to you. Well, let's go to exercise set 14.2. 14.2. There are 3 problems. So let's start. Let's solve 1 or 2 problems. 2 problems, isn't it? Okay. Let me start with the problem number 7. Problem number 2 is quite easy. There's nothing to worry about because I give clue for 2. This is y, but we have to integrate with respect to x. Keep y as a constant. But integration of dx is x. So y will be constant. X will be integrated. The limits of x is given here. Y to 3 minus y. Y to 3 minus. Now substitute upper and lower limits. You will get only the function in terms of y. Multiply this y inside and then integrate with respect to y. Apply the limits 0 to 1 to 3 over 2. That's it. So this is very easy. I'm moving to problem number 7. Problem number 7. Look, we will solve this one right now. Okay. Problem number 7. The first integral, that is the inner integral, iteratively we had to integrate one by one, isn't it? So inner integral is with respect to y, and y is involved in both the terms. Right? Okay. So what's the first step? Obviously substitution method, isn't it? Let u is equal to x is constant. Now when we integrate with respect to y, x is constant, isn't it? So x will not change. U is equal to x square minus y. So what is the du? Du will be x square will be constant is 0 for minus 2y dy. We have to differentiate with respect to y because y is the variable in discussion. Therefore we want y and dy to be clubbed. So y and dy will be negative du over 2. Let's use all this information, and we want the limits of u. Let's change the limits as well. When y is 0, this is y is 0, y is equal to x, isn't it? Y is 0 gives u is x square. U is x square. Y is equal to x. The limits of y is given here. Y is equal to x gives u is 0 because x square minus x square from here 0. So it is from x square to 0. Lower limit x square, upper limit is 0. So now what happens here is the integration is equal to now we'll start the integration. Now outer integral remains 0 to 1. Inner integral becomes x square to 0. X square to 0. This will be y and dy will be here. It's a negative du over 2. Under square root there is u. So u to the power half. That is it. So keep negative 1 over 2 outside. When you integrate, the outer integration is with 0 to 1. there is a dx outside. This inner integral is working now. Negative. So when we integrate u raised to half, you will get u raised to 3 over 2 divided by 3 over 2. Isn't it? Simplify the upper limit. Lower limit is x square, upper limit is 0 dx. And then the next step, what you get is of negative half outside. Integral 0 to 1 is outer integral. Substitute upper limit 0 for u. So 3 over 2 will be 2 over 3 outside, isn't it? The denominator. When you use 0, u will be 0, and next x square to the power 3 by 2 dx. Okay, this will be negative, and there is a negative outside, so it will be 1 over 3 integral 0 to 1 x power 3. This is x square over power 3 by 2, so this is x cube dx. It is quite easy integration. Now the answer is x raised to 4 over 4. There is a 1 over 3 outside, and from 0 to 1, it is 1 over 3 into 1 over 4, 1 over 12. Now let me try problem number 4 as well. So two integrations, isn't it? One by one. First integration is inner integration is with respect to y, and the limits of y is equal to x square, y is equal to x, isn't it? Let's solve this one. Now how to integrate this one? When we integrate with respect to y, x is constant. So this is actually root x over root y can be written as x power half over y power half, isn't it? You can still write x power half, y power negative half. So when we integrate with respect to y, x remains constant, integration only y. That's what we are going to do here. So 4 starts here. Outer integration is constant, limit 1 by 4 to 1. Inner integration takes place. So when you integrate root x remains constant. Integrate y to the power negative half. The power will be increased. Y power half plus 1 divided by negative half plus 1, isn't it? Negative. So what do you get? Y to the power half plus negative half plus 1 is positive half, isn't it? Divided by half from x square to x dx. So in the next step, this is 1 over 4 to 1 root x. Upper limit will give you again, this root x is nothing but x power half, you can write. This is x power half. 1 by 2 can be 2 outside. Now x power 2 minus y will be replaced by x square power half will be x square power half will be what? Multiply this one, it will be 1x. It will be x dx. The next step, multiply this x power half inside, so it will be 2 integral 1 over 4 to 1. When you multiply the x power 1 by 2 inside, this will be x power root x will be x minus x power 3 over 2 dx. And now ordinary single variable integration, isn't it? First term will be x square over 2, second term will be x raised to 5 over 2 divided by 5 over 2, from this 2 is constant outside, from 1 over 4 to 1. Now you can substitute one upper limit and lower limit, get the answer. Answer is 13 over 80. Fine. Next we will see a different problem. The answers are here given for all the 3 problems. We have a different problem now. Evaluate the double integral in 2 ways by using iterated integrals. Okay, 2 ways. First way, the region as type 1 region, and second, take the region as a type 2 region. So let's do it right now. Type 1 and type 2 region, isn't it? What is first? Type 1. Type 1 region, remember we integrate with respect to y first. Okay. First find the region. What is it? Y is 1, y is 2, x is 0, y equal to x. All these information should be drawn on the graph roughly. Just draw a rough graph, isn't it? This is the line y is equal to x, y is equal to 1. It's a straight line parallel to x-axis. This is x-axis. This is y-axis. Y is 2. Another line. So all the three y equal to 1, y equal to 2, y equal to x have been drawn. What is x equal to 0? X equal to 0 is y-axis itself. So which is the region bounded by all these lines? This line, this line, this line, all the 4 lines give you bounded curve. This one. This is the bounded region, isn't it? This is the bounded region. It's not the triangle, only this part. So we are supposed to find the area of this part. So now we have to start with the type 1 method. Type 1, we have to integrate type 1. How do you write for type 1? Integral, double integral, f of xy is given. What is it? What is it? F of xy. Type 1, we will start with the dy, end with the dx. So if you consider it's the type 1 region, see this part, when y is 1, this x is also 1. So this point is 1, 1, because the line is y equal to x. So this line is called x is equal to 1, which is not given, but we need to know that we need 2 regions in this direction of x, isn't it? Okay, because the upper, see, when you take a straight line roughly joining the 2 curves of y throughout the entire region, the lower limit is lower limit and upper limit are not same for this region. See, when you integrate with respect to y first, we need the limit of y as lower limit of this line and upper limit of this line, isn't it? If you roughly take a region, see, the lower limit changes after some time. Here the lower limit is y equal to 1 for this first part, but second half for this region, if you take a vertical line here, the lower limit is y is equal to x, different. That is, there are 2 regions now involved in type 1 if you convert into type 2. Region 1, rectangular, all the limits are constant. Region 2, variable, isn't it? Here y is equal to x is the lower limit. So when you want to try integrate type 1 method, we separate into 2 parts. Double integral over region 1, x y square is the function, and we know type 1 will start with the dy dx, plus on the right side another region, double integral over region 2, x y square dy dx. Integration is quite easy task. You have to find the limits, that's important. And the region 1 is taking place over a rectangular, integration 1, first double integration is taking place over the rectangular region, isn't it? So all the limits are constant. X, the limits of x will be 0 to 1 this direction, 0 to 1. Limits of y will be this one, 1 to 2. So first we write the limits of 1, which is 1 to 2 x y square dy dx, and the limit of x in the direction, all the limits are constant when you find the region is a rectangle, isn't it? 0 to 1. So first part of the integration is very easy. Second part, double integral x y square dy dx. Okay, the second part, we know when we are integrating with respect to y first, take a vertical line, vertical strip inside the region. That vertical region, vertical strip will give you tail end and head end as your lower and upper limits. tail end is on the line y is equal to x. So y limit is x here. Head end is on the line y is equal to 2. So upper limit is the constant. But one of the limit is variable is enough. So y limit is in variables. Obviously x should be constant. So x starts from 1. This end, this region starts when x is equal to 1 and ends at when y is equal to 2. At this point x should also be 2 because y and x are equal. So this line should be x is equal to 2. Therefore this is 1 to 2. So we have to separate the entire region into two portions. If the upper and lower, if there is any difference in the upper and lower limits throughout the region. See, if the region is like this, if you iterate throughout the region, upper and lower limits are same. But here, throughout the region is not. Lower limit is different for the first region and for the second region it's totally different, isn't it? So the limits have been found. I leave this work to integrate for you. You have to integrate this one, isn't it? Integration we have seen many times how to integrate. So this is the term to be integrated. And the answer is given in the problems 31 over 10. 31 over 10. Now let me show you how to do the same problem as type 2 region. See, if you want to integrate this problem in type 1 region, you need to take two different regions because the lower limit y is 2 is common upper limit, but y is equal to 1 is not the common lower limit. For the first part it is okay, but the second part it is y is equal to x. So we need to separate into two regions for type 1. But let us see what is the case in type 2. And type 2, let us see. The same graph will come again. We have to draw the same graph. This is y is equal to x, this is y is equal to 1, this is y is equal to 2. This is the region that you are looking for. But when you are dealing with the type 2, your function is xy square dx and dy, isn't it? You need the limits of x in this direction. See, when you are integrating with respect to x, you always take a horizontal line inside the region and check its tail and head ends. At the tail end x value is 0, so lower limit is 0. At the head end x value is y, x is y. That is, the limit is same throughout the region. See, lower limit is same throughout the region, x equal to 0. Upper limit is y is equal to x throughout the region. So no need to separate the region into two parts, 0 to y, obviously. And now outer limit y should be in constant. What is the maximum value of y in this region? The entire region, maximum value of y is 2, minimum value of y is 1. So y is from 1 to 2. That's it. You can integrate this one very easily than type 1. So in some cases type 2 will be good. In some cases type 1 will be easier. We can identify this one by just looking at the graph of the limits given here, right? Now integrate this one. What is it? Outer integration is 1 to 2. Inner integration, we integrate with respect to x, y square is constant. Integrate x, you get x square over 2 and the limit of x will be 0 to y. Outer integration is y. Now substitute upper limit, lower limit. 1 by 2 is constant, y square is kept as constant. So this is y square minus 0 dy. So this is nothing but 1 by 2 integral y raised to 4 dy from 1 to 2. So you will get 1 by 2 y raised to 5 over 5 from 1 to 2. So 1 by 2 into 5, 1 over 5, 2 to the power 5 minus 1 to the power 5, isn't it? So this is 1 over 10. 32 minus 1, 31 over 10, that is it. So type 2 is very easy for this kind of problems. Try this one yourself, a similar type problem. Use either type 1 or type 2 accordingly. The graph is given here for sine inverse x. So graph is given, and the function to be integrated is just x dx. You can choose as dx or dA can be either dx dy or dy dx, isn't it? You can choose dx dy, no issue. Dx dy, therefore limit of x should be variable. That is it. In this way you will take a line. Its lower limit is on the curve y is y equal to sine inverse x, therefore x is equal to sine y. X is equal to sine y. So lower limit is x equal to sine y, upper limit is x is what is the value? X is equal to 1 over root 2. X is equal to 1 over root 2. So we got it. Double integral sine y to 1 over root 2 x dx dy. And what is the limit of y? Y is the range. This is the intersection of this, isn't it? So in this range, what is y? When x is equal to 1 over root 2, substitute in this equation, you will find y. 1 over root 2 will be 4, sine inverse 1 over root 2 will be pi by 4, y will be pi by 4. So 0 to pi by 4. Integrate this one, you will get the answer. That's it. Now a different problem with the graph. Different problem. See, integration will be left to you. I will give the technical part, how to find the how to choose type 1 or type 2, and then how to identify the limits. Then integration will be left to you. Okay. First, okay, what's the problem? Y square is equal to 9 minus x. When x is 0 is the place it intersects y axis. So both will be intersecting at y x is 0, both will give you y square is 9, so y is plus or minus 3. So y is plus or minus 3 is the y intercept. That is good for both the curves, so we cannot identify the curve by this one, isn't it? But x intercept, take y is 0. Y is 0, first equation gives you x is equal to 9. So x is 9, which is larger, bigger one, isn't it? This side, this is 5, more than 5. So this curve is y square is equal to 9 minus 6. So obviously the second inner curve should be y square is 9 minus 9x. So the area bounded between these two curves will be the area we are looking for. See, now we can write the function to be integrated. See, we are asked to find the area. See, I have not given the formula of area. Area you can find area using double integral dx dy. That's it. The function is considered to be 1. If the function f of xy is taken as 1, then the volume will be equivalent to the area. See, here only the numerical value of the volume is equal to the area, not the unit. For volume, unit will be cubic units. For area, units will be square units. That's the only difference, but the data will be, the numerical value will be same. So volume will be area when the function f of xy is just 1. So that's it. So finding area using double integration. This is an application of a double integration. It's very important as well. So we are finding the area between these two curves. So let's take a horizontal strip, that is we are using type 2. Type 2, because see, if I take a horizontal strip, its lower limit is first this curve, upper limit is this curve, isn't it? The limit is same throughout the region. There is no change. Throughout the region, limit remains same. I can consider that one very easily, isn't it? So type 2, what is it? Double integral. We are finding area. So function value is 1. There is no function given in the problem. We should write dx dy or dy dx. Now find the limits of x and y using these curves. X and y, isn't it? The lower limit of this curve, this line in this region, will give you x value from this curve. Find x from this curve. What is it? X y square is equal to so how do you find x? So divided by, what is it, y square minus 9. Okay, this one I'm writing from this one, from this curve. It is given here y square is 9 minus 9x. So this is 9x is equal to 9 minus y square. What is x? X is equal to, divide by 9, 1 minus y square by 9. So this is our lower limit for x, 1 minus y square over 9. And the upper limit is in this curve, this one. Y square is 9 minus x. So x is 9 minus y square. 9 minus y square. That's right. And the maximum and minimum value of y will be in this direction. This is negative 2, 3 to positive 3. Integration is your task, isn't it? So when you integrate this one with respect to x, you will get outer limit is minus 3 to 3, positive 3 x, and the lower limit will be 1 minus y square over 9, upper limit 9 minus y square dy. Substitute upper and lower limit, simplify and integrate. Try to get the answer. The answer is 32 area square units. If it is volume, then it will be cubic units. That's the difference. That's it. So integration is your task. I have considered this as second type region, and then we found the limits from this graph. That's it. And let's see a different case of problem. This is for your practice. This problem is for your practice, because what is given here? Use double integration to find the volume of the solid. Volume. So you need a function is z. Is given here. Z is 3 minus x, isn't it? It's bounded by the cylinder x. So cylinder is, and the plane is equal to 0 to 0 3 minus x. So it will be from this information. So function to be integrated is 3 minus. If there is a function you are finding volume, so you have to choose either dy by dx or dx by ds. If type 1 or type 2 error on the ground it is a square, I mean circle. It will be you don't want actually the graph. If you want, you can drop here, because cylinder and z equal to 0, when you are on the ground, the circle is the shape, isn't it, for the cylinder, and above bounded by this plane. So on the ground, when z is 0, you are on the ground x square. So from this one you can find the limit of x and y. Substitute. If you are in type 2 region or type 1 region, it's up to you. When you want y square is 9 minus x square. Y is equal to plus or minus root of 9 minus x square. So this will be negative root of 9 minus x square, or you can, and from here partial root of 9 minus x square. And when y is 0, you can get x square is 9, x is equal to plus or minus 3. So minus 3 2 plus 3. If you integrate this one, the answer is 27 pi. Check. Integration has been left to you to practice. Okay, now this is a different kind. There are many questions possible from this kind of problems. What is it? Express the integral as an equivalent integral with the order of the integration reversal. See, order, what they mean by order is what is the variable to start with. Whether you are dealing with the type 1, this is actually type 1 given in type 1, that is start with y is inner integral, x is outer integral. So change the order, express the equivalent express the integral as an equal integral with the order of the integration reverse. So you have to reverse the order. It means you have to write the same function f of xy, but instead of dy dx you should find dx dy. See, you cannot simply change the limits. You have to find the limits to meet the type 2 region here. Draw the region by using the limits, and instead of choosing type 1 is given, you choose type 2 region, then write the limits. That's what they wanted. So let's write Let's write the limits. What is the given limit? Let me erase this information. What is the given limit? So this is y. So limits of y equal to 0, y equal to root x. Outer integral with respect to x equal to 0, x equal to 2. X equal to 0, x is equal to 2. So let's draw all this on the graph. Let's take our own graph. Rough graph. Y is root x. What is it? When you square it, it is x is equal to y square. Y is equal to root x. A rough graph. Let me get it perfect. Okay, let's draw the graph here roughly. My graph is problematic. This is y is equal to positive root x. This is y is equal to 0, which is x-axis. Another limit. So this is y is equal to 0, y is equal to root x. Both have been drawn. Next, x is equal to 0. Outer limit for x equal to 0 is this one, y-axis. This is called x equal to 0, and x is equal to 2, x equal to 1, x equal to 2. Let's draw a line here. Let this be x equal to 2. So this line is x is equal to 2. So this is the region you are working on. And now we want to integrate with respect to, so our order is changed. F of xy, instead of dy dx, we will write dx dy. So which is type 2 region. In the type 2 region, we need to consider horizontal line inside the region, horizontal strip touching both the ends. So in the lower end, so tail end, head end, the tail end, the curve is y is equal to root x. Y is equal to root x. So what is x? So x is y square. So limit of x is y square is lower limit. Head end, x value is 2. At the head end of this line, x value is 2. So the limit is from y square to 2, and this in this area y is coming up to here. What is y value here? When x is 2, substitute x equal to 2. So this at this point y value is root 2. When x equal to 2, y will be root 2. So this line is called y is root 2. So y value will be from 0 to root 2. Now you see the given interval is totally different from the interval what we have got for the second type. That's it. You are just supposed to express this one. That's it. Now one more problem to finish this chapter. Evaluate the integral by first reversing the order. See, if you integrate this problem in this given order as type 1 region, you will struggle to integrate it. You try yourself. So in this kind of cases, reversing the order, changing the order could have been very easier. So this is given type 1. We need a type 2. To start with, so double integral e raised to minus y square. I should integrate with respect to x first and then y. So limit of x, y. First draw this curve by using the limits. This is for y is equal to 4x and y is equal to 4. Roughly draw this one. X is 1, y is equal to 4x, x equal to 1, y will be 4. A line passing through this way roughly. This is y is equal to 4x, and y is equal to 4 is another line, y is equal to 4. X equal to 0, this line, x equal to 0. Y is equal to 4, y is equal to 4x, x equal to 0, x equal to 0 is this line. And what is x is equal to 1? This is x is equal to 1. The line x is equal to 1. And the bounded region is here. This is not a boundary. The y equal to 0, this x-axis is not a boundary. So this is not your region. Your region is here. And this is your region to be integrated. So in this region, you need to take horizontal line. When you are integrating with respect to x, first you need to take a horizontal line which will give you tail end and upper end. Tail end x equal to 0, head end x equal to y over head end is on this line, isn't it? So here y over 4 is equal to x, because y is equal to 4x is the line, isn't it? So upper limit is y upper limit is y over 4, and now the entire range of y will be 0 to 4, 0 to 4 in this integration. Integrate it, what do you get? You see, when you integrate, y is constant, so e raised to minus y square x from 0 to y over 4. Now auto integrate 0 to 4 dy. Okay, now I do this side. Outer integral 0 to 4 e raised to minus y square, this will be just y over 4 dy. Now 1 over 4 is a constant. Integral 0 to 4 y e raised to minus y square dy. By substitution method, you can continue. Take u is equal to y square, and du will be 2y dy. So y dy will be du by 2 e raised to minus u. So in this way, if you continue, the answer is 1 minus e raised to minus 16 over 8. You finish this problem. Thank you very much.